This is a video talking about how to do variation of parameters to solve second-order linear differential equations. A second-order linear differential equation is in the form ay double prime plus by prime plus cy equals f of t. Now, we've used undetermined coefficients to solve this kind of equation. However, f of t has to be in a particular format for this to work. It has to be either an exponential, it has to be sine, cosine, or a polynomial. So what do you do when you don't have an f of t in this form? Like secant of t, or tangent of t, or natural log of t, or t to the negative 2. Remember, that's not a polynomial. Well, not undetermined coefficients, but what we're going to do instead is variation of parameters. And let's see how to do that. So what we're going to do is, just like when we did undetermined coefficients, the first thing we're going to do is come up with a homogeneous solution, y1 and y2. And then we put together that homogeneous solution by letting c1 times y1 and add that to c2 times y2. So what we're going to do is we're going to take that y1 and y2 and multiply it by some function v1 and a different function v2. So that y1 and y2 are part of our homogeneous solutions. Those do not have the constants with them. It's just the homogeneous solutions themselves. So the question is, how do we find v1 and v2? Well, I want you to first of all put your pencil down. You're not going to be responsible for these steps. I do want to show you how we're going to come up with the equations, but it is not something that I expect you to reproduce on an exam. So, if we want to find those two variables, or really their functions, v1 and v2, we generally need two equations. If you have two unknowns, you'll need two equations. So let's take our y particular solution that we're coming up with, this v1 y1 plus v2 y2, and let's find its first derivative. When we do that using the chain rule, we get this, what I have written down here. Now, the trouble is, we've now introduced not just v1 and v2, but now we have v1 prime and v2 prime. So now instead of two unknowns, we're going to have four unknowns. It seems like a bad way to go. So what I'm going to do is say, let's make our lives easier and say that v1 prime y1 plus v2 prime y2 equals 0. That gets rid of the v1 prime and the v2 prime. Those are the two new unknowns I don't want to find. So I'm going to make sure that whatever my solution is, this is going to be true. Since again, I don't know v1 and v2, let alone v1 prime and v2 prime. So that means my y prime is now equal to v1 y1 prime plus v2 y2 prime. And I know I can find y1 prime and y2 prime because I know y1 and y2, and I can just take the derivatives. Okay, so now what? So we've got the following. We've got our original equation, ay double prime plus by prime plus cy equals f of t, and we've said we found our homogeneous solution, or homogeneous solution. And I've already said that this is what y particular is, and this is what y particular prime is. And I've said this, equation number 3, I'm letting v1 prime y1 plus v2 prime y2 equaling 0. So if I want to go ahead and plug in that yp into my original equation, I'm going to have to find yp double prime. So let's do that. That's pretty straightforward. Again, we're going to use the chain rule. And I'm going to plug this equation into star. That is, this equation right here. So when I do that, I'm going to use equation 4, equation 2, and equation 1. And then I have my entire original differential equation, that is the thing that's marked by the star. Let's rearrange this, and this isn't something you'd know to do unless you knew where the problem was going, which I do. We're going to rearrange this such that, magically, I've got my a times these two crazy things, plus v1 times ay double prime, by prime, plus cy, plus v2 times ay2 double prime, by2 prime, and cy2. Well, I know y1 and y2 solve the homogeneous solution, which means that that whole bit here And this whole bit here, well, if y1 and y2 solve my homogeneous solution, that means it equals 0. Yay, how wonderful is that? So that means I can rearrange this equation, this second derivative of yp prime. I'm going to use that to come up with this relationship. v1 prime plus y1 prime, let's say that again, v1 prime times y1 prime plus v2 prime times y2 prime is equal to my f of t divided by my constant a. That's going to be equation 5. So I've got two equations. I have the y1 v1 prime plus y2 v2 prime. I set that equal to 0. And I just went ahead and found the second equation. If I want to be able to take these two equations and solve for my two unknowns, which in this case happens to be not v1 and v2, but v1 prime and v2 prime. But luckily, I think if I find v1 prime and v2 prime, I can integrate and get back to v1 and v2. So I could use Cramer's rule, I could do a lot of algebra, but believe me, when I went through all the algebra, I would come up with these two equations. That is, v1 prime equals negative f times y2 divided by a times y1 y2 prime minus y1 prime y2. And v2 prime is similar, but it's positive instead of negative, and the numerator is f times y1 instead of f times y2. But if I look at the denominator, that looks like our old friend, the Wronskian. Yay! I know how to find a Wronskian, and that makes this equation look so much neater. So, we're going to pick our pencils back up. v1 prime is equal to negative fy2 divided by a times w, that is the Wronskian, and v2 prime is fy1 divided by a times the Wronskian. So, our goal is to find v1 and v2 because we're going to use those to build our y particular solution. We're going to have to integrate v1 prime and v2 prime to get that v1 and v2. So, here's our method. First of all, we take our differential equation, make it homogeneous or homogeneous, and find y1 and y2. We're going to say that y particular is equal to some function v1 times y1, that is part of my homogeneous solution, plus v2, some function, times y2, the second part of my homogeneous solution. I'm going to find v1 and v2 by integrating negative f times y2 divided by a times the Wronskian dt, and v2 will be the integral of fy1 divided by a times the Wronskian dt. And then we'll simply build yp with our y1, y2, v1, and v2. Let's do an example. First part should be pretty familiar. If I have y double prime plus y equals tangent of t, I know my f of t is tangent t. My a is 1. That's kind of nice. I'm going to limit this from negative pi over 2 to pi over 2 just to make life easier in my very last step. To find my homogeneous solution, I let y double prime plus y equals 0. That means my characteristic equation will be r squared plus 1 equals 0, or r squared equals negative 1, or that gives me my complex solutions, and that means my homogeneous solution is c1 times cosine t plus c2 times sine t. I'm going to let cosine t be y1 and sine t be y2. It wouldn't matter if I swap those around, but this is what I'm picking and this is what I'll stick with. I'm going to build my y particular solution to be v1 cosine t plus v2 sine t. I'm going to take the first derivative of y1 and the first derivative of y2. The reason why I'm going to do that is I know I'm going to need to calculate the Wronskian in order to find v1 and v2 because those both involve the Wronskian. Well, it turns out that the Wronskian of cosine and sine is nothing more than the lovely number 1, which is a pretty nice number to have in the denominator, especially when a is also equal to 1. So these fractions are actually not going to be fractions. So v1 is going to be equal to negative integral tan t times sine t dt, and v2 will be positive tan t times cosine t dt. And I'm not going to walk through all of this. We'll have these notes uploaded so you can look at them at leisure. But if you just see simple rewriting tangent as sine over cosine, and then splitting up fractions, because the u sub doesn't work on this left-hand side, I come up with that v1 is equal to negative natural log absolute value secant t plus tangent t plus sine t plus c, and v2 is negative cosine t plus c. These will work for no matter what I pick for c, so let's let c equal 0 because that makes things even nicer. And I have my v1 and v2 as here. Now I'm going to plug those back into my y particular solution. So I'm going to take v1 and multiply it by y1. I'm going to add, but v2 is negative, v2 times y2. And when I do that and combine like terms, I get my final answer that the y particular solution is negative natural log secant t plus tangent t all times cosine t. And because I limited t to go from negative pi over 2 to pi over 2, we can actually drop the absolute value bars. My final solution, of course, I'd have my y1 and my y2 multiplied by c1 and c2 respectively, and then add my y particular solution. So this would be my final solution using the method of variation of parameters. I could not have guessed that y particular solution like I did with my undetermined coefficients. So when you're stuck with something you can't use undetermined coefficients for, you can use variation of parameters. Keep in mind, even if I could use undetermined coefficients, variation of parameters always works. It's kind of like when we were factoring quadratics. Even if it was perfectly factorable, if you were stuck, you could always use the quadratic equation, even though it was more work, and get the right answer. Same thing with variation of parameters. It will work no matter what your f of t is.